Okay, welcome back to the last day of the conference. It's our pleasure to hear Semyon talking about the Hall effect and
quantum Hall states and on hyperbolic surfaces.
thank you for introducing yourself.
So, I would like to thank the organizers for this wonderful conference and for not forgetting to invite me. So I would like to talk about maybe work which is not very recent and at some point more recent work. So I will start with, I will not start immediately with what is quantum Hall states. I will start with something maybe more appropriate for the conference, given that people like people like probability and people like regularized determinants. So I will begin with that side of the story. So there is something called Wiegmann conjecture. Have you heard about this? Oh, excellent. All right. So that's really interesting. So this is the paper of Zabrod and Wiegmann in 2006, but I will follow the book of Scherfati from last year. She had lecture notes, and I will use notations from there. So we take n particles in the plane, in this plane. We will have a potential. So I will take a potential, very nice convex function. So it's going to be, to understand the phenomenon, we'll take C infinity, C real value. It's called external potential, and then we consider the Coulomb gas. Probability measure on endpoints, configurations of endpoints in the plane, and these endpoints are in external potential V, such that, so there is a Lebesgue measure for each of the particles. So V should be something like this. There are more examples where V can be a bit singular, have logarithmic singularities. But to understand the phenomenon, let's say it's a nice potential such that this is a probability measure for finite n, and this guy converges. And we will call it partition function. Beta here is a real number in principle. I think it might be, I think it's, let's say it's beta greater than 0. Maybe beta greater than 1. And so the conjecture is about studying Cn as n goes to infinity. Alright? So what does it say? So we will look at log n as an asymptotic expansion, n goes to infinity. And there is going to be structure something like that. Plus some boundary terms. I will explain what all this means. Plus constants. Plus terms of order small o. Wow. And now I will say what these constants are. So there is a functional called functional probability measures called algorithmic energy. Double integral. It has a minimizer called equilibrium measure. So basically, you can think of this as particles which don't like to be close by, because if they're close by, this vanishes. There's no probability to be close by.
Are you sure it's 2 beta?
Yeah, so the notations are
Usually it's
better in probability notations.
Yes. Beta equal
And,
1 is G, in the line should be GOE.
Right, so for me, beta equal 1 should be special. And actually all the talk will be beta equal 1. It's a case of determinantal case.
Yeah, so the
So in
determinantal case.
probability literature, this is called gamma.
No, this is called beta and it is equal to 2 in the determinantal case. But okay.
Yeah, sometimes it's called beta.
Once we understand each other,
Yeah,
it's fine.
you're right. You're completely right, yeah.
Okay. I just wanted to make sure that you meant what you want.
For some very important reasons, I like.
That's fine.
Right. So, and this equilibrium measure, maybe it's. Yeah. So I started saying that particles don't like to be close by, so they will be a little bit apart. It's like you put in particles here, and they will form a droplet, and this droplet will have support. Let's put ourselves in the case where this droplet is simply connected, bounded, nothing special, some domain on the plane. More general situations are allowed. How general is not clear, but pretty. And so this measure is supported on this droplet. This is complete line in my picture. And the first coefficient, B2, is just a value of this functional, of this droplet.
So the droplet is determined by V individually?
It's determined by V.
Yeah, it's not explicit, is it?
By V and beta.
And beta. It's, let's take V is equal to absolute value Z squared. It's going to be a disk. In a real case, if everything is real, you have Wiegmann semicircle. Alright, so this,
Probability will multiply V by beta. Then it does not depend on V.
So now, E1. This is interesting. This is called entropy. And it looks like this. Integral. This is like mu log mu sort of type the things which I would call entropy function. Now, I said I have a droplet. Droplet has a boundary. There are some boundary terms. Boundary terms begin at the order square root of n. Why? Because here you have n particles, you fill the droplet. So area is of order n, boundary is of order square root of n. So there will be some terms, not only integer power. Constants. Constants are the things which don't depend on potential. I'm not going to write them down, there are some constants. There's constant 1/2 n log n, sort of things like that. And we get to the phenomenon. The phenomenon is that B0 is given by minus 1/2 log det prime Laplacian. So you take the external domain. You cut out the droplet and you take external Laplacian and external. And there's going to be a little bit coefficient, which I copy from Silver's book. Excellent. I don't want to open the page. So there will be a coefficient. That's why paper notes are better. Again, it's in the beginning of the book. So maybe I write it down by memory, so something like that. And here the functional is going to look like gradient of log v, this thing squared, v mu v. Something like that. So now this is the phenomenon that is going to be determined of. That's a conjecture.
What is the condition on the Laplacian?
Dirichlet.
What do you put the prime then?
You actually don't need prime because it has no zero.
No.
Sorry, how do you define this as all unbounded domain?
So the way to define it is a bit tricky. You have to basically define it through determinant in the droplet, in the boundary. Because there is a formula that the sum of determinant log that here plus log that here is the determinant of this jump operator. So basically, if you look at the literature, they tend to define this through the determinant of Laplacian and the bounded domain plus some correction. But it looks nicer this way. All right, so why do we love determinants? Okay? At this conference, we heard many about determinants, and they are important because let me just final remark, literature remark. All this is known, I will cite Fati for the most recent work, the completed first tutor. This is not, no, well, apart from some constants.
So do these constants depend on n?
Yes. They depend on n, yes.
So they're not.
There is like minus 1/2 n log n. They depend on beta, but they don't depend on v.
Yeah.
The constant in V.
Constant in V. Not.
Constant of v. Constant as a, in the sense that it's independently some sort of universal. Might depend on the Euler characteristic of a droplet in case if it's multiply connected. But I said let's make it simple. So the determinant of Laplacian is important because it's a partition function. That's why it's important. Now, this object, I don't know how to define it properly. And I don't know how. But I'm going to say what this partition function is. So J5 you take Pn, so you take Laplacian. But let's say we're on the Riemann surface, compact Riemann surface, M metric G, we have Laplacian, we have its eigenvalues, eigenfunctions, the basis, and we say we take sum from n goes to 0 to n, a n 0 to the square root of lambda, space 1. Okay. I find that on the basis lambda and eigenvalues, a n are ID Gaussians. And then you send n to infinity, and this goes to some object which is a distribution valued random field. Right, so I refer to Ellen's book, Rami's lectures for precise definitions. So partition function, we have to be able to define partition. So it's a that's right. It's a path integral. So it's a sort of integral over exponential minus Dirichlet action. So I'm going to write phi n box phi n. And I'm going to write product from 1 to n d. So I take the Dirichlet action and I integrate over all the coefficients. And I have to insert square root of lambda in there. When all is said and done, this is an squared for each n. And what's left is product from given quality, product lambda n from 1 to n, minus 1. So minus 1, so logarithm of that n, we have to compare, it's minus 1/2, product of the eigenvalues. Product of the eigenvalues you want to call determinant of Laplace. In more rigorous terms, oops, so I think they should go up. You make a spectral zeta function. Spectral zeta function is a sum from 1 to infinity. Lambda 1 over 2 power s. You take log that prime of the opposite. So prime is because I throw away 0 mod, lambda 0 I throw away. Is defined as, so I take minus zeta prime at 0. So this admits meromorphic continuation, and this actually makes sense. Derivative at 0 makes sense. Now, so basically, why this conjecture is interesting is because there is free field hidden somewhere. In the story above, there is free field. Where it's hidden, I don't know. But it's must be there. And if you have system of many particles, then to infinity it tends to some quantum field theory. In general law is like that, so it might be one may say like that. All right. Now, what do we know? So in order to simplify the problem, I'm going to set beta equal to 1, because this turns out to be determinant case. And I'm going to replace C by a complex Riemann surface. So how the hell does that simplify the complex plane? Well, actually, the difficulty is the boundary. You don't want to deal with the boundary, the first approximation, right? So I want to do the same setting, but on a Riemann surface, like a sphere, torus. Yes.
Is C remove sigma in the if you solve the Laughlin equation on the C remove sigma in the eigenvalue is discrete.
Right. Where? Here, yes.
To define the determinant of Laughlin, you consider C remove sigma in the eigenvalue is discrete.
Here it's unbounded, so I think it's continuous, right, spectrum. So it's nothing like product of, it's more cryptic object. So the way to define this, you have to. I think maybe you have to divide. Yeah, to regularize, you probably divide it by determinant of Laplacian on C. Right, so there is a whole business to define this. Yeah, you remove the, right, yeah, you regularize. It's some sort of regularization procedure how to define this properly. So it's not literally you take product of continuous eigenvalues. No, it's a bit, you do it from heat kernel, you take some regularization. So now, exactly for this reason, I want to go to compact Riemann surface to avoid, continuous things, even though it will be unavoidable. So now, what I use is that okay, van der Waals product formula. Right? So if we go to if we're going to replace M, we better understand that object through the determinant of polynomials. And holomorphic polynomials on the Riemann surface become sections of holomorphic line bounding. So I have Riemann surface. I give myself some metric, and I have holomorphic line bundle. Of degree k. Hk is Hermitian metric. Now the Persian class of this line bundle is minus dd bar log of hk. So it's an element of h11 on m. And the meaning of degree, there are several meanings. One of the meanings is that if we integrate this Persian class, which is 1, form on the surface, and we divide it maybe by 2p, it's going to be integer k. So k is positive integer. All right? So what does it mean? So, okay, you know, we had many talks about Young-Mills theory, so basically take rank 1 vector bundle, that's your len bundle, okay? But okay, more appropriate for my talk, I'm gonna give you an example which I will use, and not, you know, it will be enough to understand. So the holomorphic line bundle, it has a basis of sections, it has holomorphic sections. So these are analogs of polynomials. Polynomials of degree k. So there are no holomorphic functions, no holomorphic polynomials, but if you allow, if you replace functions by sections, that means you have your surface and you define some sort of polynomial function locally here and polynomial function locally here. In this business, you allow at the intersection to multiply your function by non-vanishing holomorphic function. And this way, it gives you some flexibility. So the prototypical example, which I will use, is Riemann sphere. I have a coordinate z, which comes from a complex plane, in my holomorphic sections. These are just powers of z, and runs from 0 to k. Now, these guys are defined everywhere except at infinity. But because infinity is 1 point, I must say what happens. So I have my sphere covered by 2 charts. One is C, where Z lives, and one is at infinity. But so I have to tell you what this section is at infinity. Right? For each of these sections, I have to calculate transversal at infinity. But I'm going to cheat a little bit, and I say infinity is just 1 point. Since I'm going to integrate everything, 1 point doesn't matter for integration. So my sections will be just defined like that. Okay? 1 point will not matter. What happens at that point will not matter for integration. Okay? Now, the hash k function is 1 over 1 plus this to the power k. So if you take minus dd bar, so dd bar is derivative with respect to z, derivative with respect to z bar. Okay? Logarithm hk. This should give k z squared. Probably squared. And the integral a d to z of 1 plus squared over c hat, but it's the same as the integral over c, because I removed 1 point. Nothing. Is going to be equal to k. That's the concrete example of the metric. And this volume form on the sphere is called Fubini study, or round volume form. All right, and the definition of this partition function on the Riemann surface will be inspired by that van der Monte identity. So I'm going to say first that the basis of sections Sn on a surface M of genus G. Genus I used H and G kappa. Alpha is K plus 1 minus alpha dimension. So, on a Riemann surface, if alpha is equal to 0, the basis is dimension K plus 1. Well, let's check. I wrote the basis explicitly there. You see there are K plus 1 sections. So I take a section, number J in my basis at a point zk, and I take determinant. This is a square matrix. Jk runs from 1 to n equal to k plus 1 minus 1. Okay? Oops, k. J L. So this means determinant is a sum over all the permutations S x1 z sigma 1 s2 z sigma 2 etc. Sn z sigma 2. Epsilon is signature of the permutation. So this is called fermionic wave function. Any system of n fermions without interaction will have wave functions like that. Now, moreover, in this situation we have that S is holomorphic. That is particular fermionic wave function which is called quantum Hall state. That's what I studied.
The dimension is only for K1. Riemann.
So for K large enough, maybe starting from 2G minus 2 alpha minus 1. N will be, genus will be fixed, N will go to infinity, so K will be large. So now I take this determinant, I multiply it by its conjugate, and for each point I compute the Hermitian metric. For each Z1, Z2, Z3, H determinant product J runs from 1 to H Z. This is a scalar function on inputs, which I can integrate now with respect to my product. Vn the integral over the Mn and I take volume forms for each. And this is the analog of my Coulomb gas partition function for beta equal to 1, for Krivon surface.
Is it obvious it's finite?
So it's obvious that it's finite for any n. This is holomorphic, and this grows sufficiently fast at infinity
Okay.
that this converges for finite n. Now, the miracle, I said is determinantal. That's because there is a miracle. This miracle is called Cauchy DNA formula. This integral is equal to determinant of a gram matrix of the basis of my basis conception. L2. This is purely combinatorial identity, which you can find on Wikipedia for vector spaces for with norms. Here it's L2 norms.
L2 with respect to what?
So L2 is so you take integral and you compute first the Hermitian metric of SS prime at a point z. It will depend on the point, and then you integrate this with respect to the volume. This is L2 structure. So this is why experimental case is always easier compared to general case. So now
Still an n by n matrix, right?
this is n by n.
Yes.
Yeah, still n by n matrix,
So simple.
still determinant, but
You
it's
still need to do something.
it's still some work. Yes, absolutely. So we need more miracles. Yeah, that's right.
It's a beginning.
It's the beginning of now.
So is there only one holomorphic line bundle of degree k with the Hermitian metric?
So it's actually the line bundles of degree k. They come with a moduli space, which is 2 g-dimensional torus. Here I fixed one. I didn't tell you, but I fixed some.
Okay, so
That
Z
moduli
is
space.
internal, so it's,
In principle, I could vary the line bundle, and I do. I could vary the complete structure on the surface, but let's say it's fixed this for
okay.
to define this, but then I want to vary it, definitely, absolutely. Now, I said this is a wave function of fermions. So wave functions, they have the property that they not only in L2, they actually normalized. The norm of the wave function is 1. So if I started with wave functions which are normalized, this matrix is identity matrix. This determinant is equal to 1 identically. So my Zn is 1. So I have to do something a little bit to say why what I compute is not just log of 1. Right? And the way it works, so I take Sn to be ONB for some fixed metric H0, okay, and the metric G0 on the surface. This is metric on a line bundle, this is metric on the surface. And I introduce H as a relative metric. So this is going to be the minus k phi. Phi is a function, a real function on a surface. Phi should be, so I should have the property that dd bar log, basically I should have the property that the 1 dd bar log H is positive, definite, minus dd bar log H is a positive, definite 114. So this translates into the condition on phi, which is akin to phi being subharmonic function. So if we plug H here, it's going to be d bar log H0 plus d bar phi is positive. So dd bar phi is subharmonic compared to this form, this standard condition. So this is the analog. Before I had Coulomb gas, I said V is like convex like that. So this is the analog that it's kind of, you know.
Is there an I factor? Is there an I factor missing?
Yeah, maybe I. It may be, yeah, maybe this should be understood as multiplied by I dz as a form.
Yes.
As a one form you multiply.
Yes.
Yeah. All right. Now so we obtain an object which depends on a pair of Hermitian matrix and on a pair of Riemannian matrix. So this reminds you of the Liouville functional in CFT, in Gaussian free field. In Gaussian free field, you have this comparison formula, right? So log Z. So you have two metrics. One in a conformal class of G0, and another metric is G0. You compute G0, right? The two metrics in the same conformal class, you compute the ratio. What do you get? You get 1 over 6 Liouville action. So Liouville action is grad. Now, my theorem will be that there is a comparison formula for my partition function over here. So the comparison formula, so I'm going to make another choice that the minus dd bar log h is equal exactly to the Kähler class of the metric G. So my Hermitian metric and Riemannian metric will not be independent.
Semyon, I lost track of something. When you fix H0 and G0, then your L2 product involves what? When you compute this one here.
Yeah, this L2 product involves H and G. But this is OMB for H0 and G0. So this is no longer normalized. This matrix is no longer identity matrix.
Okay, so all H and G.
Everything starts to. If I set phi to 0, G equal to G0, it's 1. If not, it starts to deviate from being diagonal. That's a game. So logarithm of Zn. So I call everything Zn. So admits an asymptotic function. So there is going to be 3 terms. K squared. So expansion is actually in K rather than in A. First functional is called Aubameyang functional. Second functional is called Mabuchi functional. And here you have Liouville functional. But Liouville functional written in terms of phi, not in terms of conformal class, but in terms of kilometric. Same functional, but different notations, different code. So let's see if you recognize this functional. So this is just Dirichlet type, Dirichlet type functional. This one is volume form of Vg, volume form of Vg0. So this is easier to recognize. This looks exactly like entropy before in Coulomb gas. This is exactly entropy. And this one, actually, if you take logarithmic energy and you differentiate twice by parts, you will obtain Dirichlet type function. So this is kind of analog of
So
logarithm.
this you can see as an integral against equilibrium measure.
Yes, yeah, this we can see that.
The curvature is constant.
Huh?
Your curvature is constant for G0.
No, not necessarily.
They look like the wave function, but you have 1/2.
They look like
It looks like the wave functional, but you have 1/2 curvature.
it's 1/2. Yeah, there is no curvature here. There is no, it's not Liouville. It's different. This one it's very similar, but it's like Liouville but for phi. Liouville is actually for sigma. So you have to solve this is equal to G for the Kähler potential, plug it into Liouville, and you obtain Liouville function. I don't do it in here. But, all right. So this is the analog. Is clear, right? Yeah.
Can you say what is the equilibrium measure in your sample?
So here the
Is it
so here I can say exactly what's going on. The droplet takes all the sphere,
and it's going to be new?
and it's going to be distributed according to the so the density as n goes to infinity tends to constant.
Yeah.
Plus corrections with dependent curvature.
The density with respect to?
The density
Zero?
with respect to G. With respect to G. To the G and H. So the density function.
Okay.
The density function. Which you integrate with respect to the G.
It's unrelated to G0.
G0 is related to G by d bar of phi.
Just a parametrization.
Okay.
It's a little, yeah.
Okay.
Now, you can wonder, so we see Liouville comparison formula. Can you actually see the determinant? Because comparison is not the same as the determinant itself. And we actually can. For this, you need to actually not pick Sn, pick some OMB basis with respect to some metric, but just find the basis on the street. Just find like some simple basis. And this simple basis, in all the examples, it turns out to be this basis of which I wrote before on the Riemann sphere. Just monomials in the end. And so we did. So you can actually do determinant on a sphere, on a torus, round sphere, flat torus. This actually works on a conic singularities. If there is a disk with a conical singularity, you obtain the determinant just by computing this guys into infinity. You obtain the implicit form of determinant of Laplacian for singular case. So that's why I say that conditions it could be it cannot meet singularity. There is a case where there is a sphere with two opposite conical singularities. And more recently, we looked with Paul Wiegmann at the hyperbolic case.
Here, it's a variation formula. Right?
It's a variational formula.
So there should be a log Zn G0, but it's one. It's 0 because Zn G0 is 1. You said, or
So if you set phi to 0, all these functions vanish. The left hand side is log 1.
And log 1 is that was just for confirmation.
Yeah, it works. So So the hyperbolic, we did hyperbolic cylinder. Hyperbolic cylinder, you have two ways to describe it. So you take a disk of radius 1, and you cut a smaller disk. So this is on a complex plane. This smaller disk is this is e to the minus p over L. So this unknown annulus. And the hyperbolic metric, the hyperbolic is L squared, C squared, hyperbolic form. Looks like this. Times. So you can check that this is indeed hyperbolic. The d bar log of that guy equal to minus that guy. This metric has hyperbolic curvature. It's infinitarian, it's non-compact. So you can also map it to the hyperbolic upper half plane with the metric. And it's gonna be like the part of between two semicircles. And so this corresponds to hyperbolic half plane with the group gamma, which takes Z into the EL. So it identifies. All right. So here's the formula. So the peculiarity here it's a non-compact case. So we again back into the non-compact case, right? So everything non-compact. And peculiarity is that the space of sections, of two sections, is the n, where n actually takes values negative and positive. Can go from minus infinity to plus infinity. Because all these monomials are L2. I cut out 0, so there is no problem with convergence at 0. So Z n is defined before, so it's determined with grand matrix. So this is my Sn. And I will write the formula. So, log Zn is n plus infinity. P over L over 2 squared minus P L. This is Zelberg zeta function. So Zelberg zeta function for the annulus is a product from 1 to infinity. So you should really think about this as a hyperbolic cylinder. It has one central closed primitive geodesic. Zeta function in general it involves product of all primitive geodesics. Here is just one. Right? So it involves one infinite product. E to the minus 2p L n plus b over 2. So we see, first time we see the Hilbert zeta function arising from these formulas. Not hard calculation, but we were kind of happy. So I didn't say what b is because before I had k. So my d bar. So my Hermitian metric here. So d bar log hk minus 1 is equal to g hyperbolic times I dz bar. And I think h has something like the form of 1 over sine some such form. And k is b, so I don't know why I introduced notation b. B is magnetic field, because this corresponds to the electrons in magnetic field. And in the language of line bundles, it corresponds to line bundle of degree k. So k is magnetic field. Sorry, I changed my notations in the middle, but b is just a k. So, what the hell is that?
Sorry.
Yeah.
B is K, what is N?
So n is, sorry, I said I have infinite number of sections, and we take, I start from minus n to big N. I take,
It's not related. Okay. Before
yeah,
N and K.
before they were related. Now they are not. Now these are two separate numbers. They don't go to infinity together. So in the limit I obtain the thing which depends on magnetic field. I just check if I get the constant right. No, constants have to be right. Now what is this? Why is it a determinant? So it's actually,
Sorry,
yeah.
where does B happen to, where do you see B in the metric? You don't see.
So here, so the Hermitian metric, I do not, and then I integrate over my surface. So this is actually determinant of a magnetic Laplacian on that. So magnetic Laplacian, in this case, on a Riemann surface, it's a Laplacian which acts on forms, on the tensors, if you want, on sections of line bundle. In this case, it's actually Laplacian on functions. And I'm going to write it in the coordinates of the upper half plane because it has the easiest form. So it looks like y squared e2 by dx squared e2 by dy squared minus 2I dy d by dx. This is a Laplacian, but not scalar. So this thing, and I think I run out of